If you pick up a real diamond, like a completely unmounted raw diamond, and hold it against your skin, it feels cold.
Oh yeah, it feels like actual ice.
Right. It instantly, almost aggressively steals the heat right out of your body.
It really does.
But here's the completely bizarre paradox about that. If you look at the actual atomic physics of that exact same diamond, it thinks your comfortable 70-degree living room is a freezing, desolate Arctic wasteland.
Yeah, it's a completely different reality.
Literally. The physical gemstone in your hand operates in a totally different thermal universe than, the metal ring it might be mounted on or the wooden table you just set it down on.
It's honestly one of the most beautiful hidden realities in the physical world. I mean, we use the word temperature every single day to describe just completely mundane things.
Right, like your coffee getting cold.
Exactly. You complain about cold coffee, you check the weather app on your phone, you wait for the oven to preheat.
Yeah.
We treat temperature like this universal democratic baseline. We just assume 70 degrees feels like 70 degrees to everything in the room.
Because to us, it does.
Right. But hiding right beneath that incredibly mundane concept is this violent, chaotic universe where quantum mechanics basically crashes headfirst into the physical properties of matter.
Which is wild to think about.
It is. The microscopic dance of atoms dictates the macroscopic heat you actually feel with your own hands. And every single material dances to a completely different set of rules.
So, welcome to this deep dive. Today, we are decoding one of the most significant foundational hurdles in the entire history of solid-state physics and materials science.
It's a concept called the Debbie temperature.
The Debbie temperature. And the clear goal today for you listening is to give you a whole new lens through which to look at the physical world.
A completely new perspective.
Exactly. We are going to explore how human beings actually figured out the exact mechanical gears of how heat works.
Which was not easy.
Not at all. We are going to track this massive scientific crisis that literally stumped Albert Einstein.
Yeah, Einstein himself.
Then we'll look at a brilliant breakthrough by a physicist named Peter Debye. And ultimately, we're going to build a literal thermal ruler from scratch.
I love that analogy, the thermal ruler.
Right. By the time we're done today, you will understand exactly why that diamond feels so cold and why heavy metals and sparkling gemstones experience the exact same room temperature in completely opposite ways.
So to really understand this, we have to travel back a bit. We need to go back to the early 20th century.
Yeah, set the stage for us.
Well, physics was in a state of absolute upheaval at the time. For a very long time, classical physics had a pretty straightforward, comfortable rule for how solid materials, like metals or crystals, handled heat.
Right.
It revolved around a concept called specific heat.
Okay, let's unpack this right out of the gate. Specific heat. It is essentially a measure of a material's capacity to store heat when its temperature is raised, right?
Exactly. Think of it like a thermal sponge.
Thermal sponge, okay.
Yeah, if you have a sponge, you want to know how much water it can soak up before it's completely saturated and the water just starts spilling over the sides.
Makes sense.
Specific heat is the fundamental question of, if I want to raise the temperature of this solid block of material by exactly 1 degree, how much thermal energy do I physically need to pump into it?
And classical physics had an answer for that.
Well, they did. Specifically, there was this rule formulated in 1819 called the Dulong-Petit law.
Dulong-Petit, okay.
And it basically stated that as you pumped heat into a solid, its specific heat, its capacity to hold that energy remained essentially constant.
Wait, so the thermal sponge was basically infinite?
Exactly. No matter how hot or how cold the material was, it took the same amount of energy to raise it 1 more degree.
Okay.
And for decades, this seemed perfectly true. Because, scientists in the 19th century were mostly measuring things at room temperature or higher.
Right, they were boiling water, heating metals, and blacksmith forges, that sort of thing.
Right. And the math held up beautifully in those everyday warm conditions.
But then technology caught up, as it always does.
As it always does, yes.
As laboratory equipment got vastly more sophisticated near the turn of the 20th century, physicists finally gained the ability to super cool materials.
This is where things get messy.
Right. They started dragging metals and crystals down to extreme, punishing temperatures, like getting closer and closer to absolute zero.
Which is the theoretical point where all molecular motion just completely stops.
Exactly. And when they brought matter down into this deep freeze, the classical rules just simply shattered.
They totally broke down.
The specific heat didn't stay constant at all. it plummeted.
The thermal sponge suddenly couldn't hold any water at all.
Right. It suddenly took drastically less energy to raise the temperature of a freezing material by 1 degree than it did at room temperature.
Which makes no sense under the old rules. The material just completely stopped behaving the way centuries of math said it should.
Because a cold atom is still the same atom as a warm atom.
Right, exactly. The drop-off was massive, and classical physics had absolutely no explanation for why a cold atom would behave any differently.
They are the exact same atoms.
Right. Why would their capacity to absorb energy suddenly just vanish simply because they were cold?
It's a total paradox.
It was a massive crisis. It threatened the entire foundation of thermodynamics at the time.
Which brings a rather famous name into our story.
Oh, yeah?
Albert Einstein looks at this broken classical rule, and he decides he's going to attempt to fix it.
This is around 1907. He's fresh off his miracle year, where he published papers that literally changed the world.
Right, the guy's on a roll.
Exactly. So now he turns his attention to solid matter, and he formulates what becomes known in physics history as the Einstein model.
The Einstein model. So what was his big idea here?
Well, Einstein was trying to apply the brand new, highly controversial theories of quantum mechanics to solid matter.
Okay.
Max Planck had just recently proposed that energy isn't a continuous smooth flow like water coming out of a hose.
Right, it's not a stream.
Exactly. Planck said it rather comes in little discrete, indivisible packets or quanta.
Like sand pouring from a bucket instead of water.
That's a great way to put it. So Einstein took that quantum idea and applied it directly to the vibrating atoms inside a crystal.
He theorized that every single atom inside that solid crystal lattice was acting as an independent harmonic oscillator.
Yes.
Let's translate that into a physical picture for everyone.
Please do.
He is essentially imagining a dense room full of people, and every single person in that room is on their own individual pogo stick.
I love the pogo stick analogy.
Right. Every person representing a single atom is just jumping up and down, vibrating in their own specific spot.
Mm-hmm.
And the crucial defining characteristic of Einstein's model is that word, independent.
That is the key word, independent.
They are completely disconnected from their neighbors. They are all jumping to their own rhythm at the exact same frequency, just completely ignoring the atom right next to them.
Right. And by treating them as perfectly independent little pogo sticks, he could apply incredibly elegant, simple mathematics to calculate their total energy.
Because they don't interact.
Exactly. He isolated the variables. If you treat a billion atoms as 1 billion separate, non-interacting math problems, you could just solve one and multiply it by a billion.
Oh, wow. That is mathematically gorgeous.
It is. It's so clean.
But wait, let's think about the physical reality of a solid object here. Say, a solid block of iron.
Okay.
Those iron atoms are densely packed. They form a rigid, highly structured crystal block.
Yep.
How could they possibly not affect each other? I mean, if I have a room packed shoulder to shoulder with people on pogo sticks and one person starts bouncing wildly,
They're going to bump into the person next to them.
obviously, the vibration has to transfer. The idea that they are independent seems completely counterintuitive to what a solid actually physically is.
So what's fascinating here is that your intuition is spotting the exact fatal flaw of the entire model.
Oh,
Yes. But we have to give Einstein a little credit for why he made that assumption in the first place.
fair enough.
If you acknowledge that billions of atoms are all pulling, pushing, and crashing into each other simultaneously, the math becomes a chaotic, unsolvable nightmare.
It just gets too complex.
Way too complex. It's what physicists call a many-body problem.
A mini-body problem.
Right. At the time, they simply didn't have the mathematical tools to calculate the interactions of a trillion connected springs.
So he just simplified it on purpose.
Precisely. Einstein made a deliberate, brilliant simplification. He essentially said, let's pretend they don't interact, apply this new quantum theory, and see if it gets us closer to the truth than classical physics did.
And for a while, it seemed like a massive triumph, didn't it?
It really did. At higher temperatures, Einstein's calculations matched the experimental data beautifully.
Wow.
He successfully proved that quantum mechanics actually applied to solid matter. He proved that atomic vibrations were quantized.
So it was a huge deal.
It was a monumental achievement that changed physics forever.
But the victory was short-lived,
Very short-lived.
because the true test of the model was in the extreme chill of the laboratory, the exact place where classical physics had broken down in the first place.
Right, down near absolute zero.
Exactly. When experimental physicists brought actual materials down to those extremely low temperatures near absolute zero and compared the specific heat to Einstein's new formula,
It failed.
it just completely diverged from reality.
Yeah, I mean, it was better than the classical model, sure, but it still completely missed the mark.
How so?
Well, Einstein's theoretical curve predicted that the specific heat would drop to zero incredibly sharply.
Yeah.
Just plummet.
Like falling off a cliff.
Exactly. But the actual observed experimental data showed the material holding onto its heat capacity just a little bit longer. The drop-off in reality was much more gradual, following a curve that Einstein's math simply couldn't produce.
So the independent pogo stick model fell apart when things got freezing cold.
It completely fell apart.
Einstein, literally one of the greatest minds in human history, hit a wall.
He isolated the atoms to make the math beautiful, but nature refused to be isolated.
Which makes sense. Nature doesn't care about our math being easy.
Not at all. And this failure created a massive, glaring gap in scientific understanding.
It proved beyond a shadow of a doubt that you simply cannot ignore the connections between atoms.
No, you can't.
To fix the math and to truly understand how heat works in a solid, science needed a completely reversed way of thinking about things.
They needed to stop looking at individual atoms and start looking at the collective.
Which brings us to the next act of our drama. This is where a physicist named Peter Dubhe enters the narrative.
And he completely rewrites the paradigm.
If Einstein's model was the brilliant but flawed rough draft, Dubhe comes in with the red pen and provides the definitive answer.
That's a great way to look at it. He introduces what we now call the Dubhe model.
And his core argument is exactly what you pointed out earlier. Atoms in a crystal are solid, they're bound together.
Right.
Therefore, vibrating in isolation is a literal physical impossibility.
Dubhe looks at the crystal and basically says, these are not independent pogo sticks. This is a massive, three-dimensional web of springs.
Oh, a web of springs.
Yes, every single atom is tightly connected to its neighbors by atomic bonds.
Right.
If you pluck one spring, if you introduce a little bit of heat energy to one atom, that vibration doesn't just stay localized.
It has nowhere to go but outward.
Exactly. It ripples through the springs. Dubhe realized that heat is not individual atoms shivering in place.
So what is it?
Heat is collective movement.
Collective movement. This introduces a concept that is absolutely central to modern material science, doesn't it?
It does. It introduces the phonon.
Phonons. P-H-O-N-O-N.
Right. We often hear about photons with a T, which are packets of light.
Like in lasers or sunlight.
Exactly. But a phonon with an N is a packet of sound or a packet of vibrational energy.
Okay.
Material scientists refer to these as lattice vibration.
So instead of thinking of heat as, like, a localized fire inside the material, we have to think of heat traveling through a crystal as continuous interconnected waves.
That is the perfect visualization. When you touch a hot stove, the heat travels from the metal into your hand.
Right.
Not because individual metal atoms are physically migrating from the stove into your skin.
That would be terrifying.
It would. No, it travels because a wave of vibrational energy is propagating through the interconnected web of the metal.
Oh, I see.
A phonon is essentially a quantized ripple of that exact energy.
So Dubhe shifted the entire conversation.
He completely flipped it. He took it from Einstein's individual kinetic energy to collective wave propagation.
He married the quantum idea of discrete energy packets with the continuum mechanics of elasticity and waves.
He really did. It was brilliant.
But Dubhe didn't just say, oh, heat is a wave. He introduced a crucial, absolute limitation to these waves, didn't he?
He did. And this is the concept that really forces you to bend your mind around physical reality.
Yeah, this part is wild.
Dubhe recognized that a crystal, no matter how massive it is, whether it's a microscopic grain of salt or a diamond the size of a baseball,
Right.
is essentially a box.
A box.
Yes.
Right.
It is a confined geometric space containing a finite, limited number of atoms.
Okay, finite atoms.
And because of that unchangeable physical reality, there is a strict mathematical limit to how finely or rapidly these collective waves can vibrate.
Wait, really?
Yes, there is an absolute upper speed limit to heat.
An upper speed limit to heat.
In physics, this is called the Debye maximum frequency.
The maximum frequency.
This is the absolute cornerstone of his entire model. It is the key to solving the whole mystery.
Okay, I have to stop you there because I need to challenge this concept of a speed limit.
Go for it.
If I have a box of atoms, right, and I hook it up to an infinite power source,
Okay.
and I just keep pumping more and more and more thermal energy into it.
Sure.
Energy can't just disappear. The laws of thermodynamics completely forbid it. So if I am pumping massive amounts of energy in, why can't the atoms just vibrate faster and faster to absorb it?
It seems like they should be able to.
Right. Why can't the wave just get infinitely smaller and more rapid?
Because eventually, you literally run out of physical atoms to carry the wave.
Make it make sense.
Think of it like trying to draw a highly detailed curved line on a very low-resolution computer monitor.
Okay, like an old 8-bit screen.
Exactly. A monitor is made of discrete pixels.
Right.
If you try to draw a curve that requires details smaller than a single pixel, the monitor simply cannot display it.
Because the pixels are too big.
Right, it physically lacks the resolution. A crystal is exactly the same. It is not a continuous, perfectly smooth jelly.
Oh, I see.
It is made of discrete, individual atoms spaced at specific distances.
So the atomic lattice is essentially the pixel grid.
Exactly. A thermal wave has to physically map onto those atoms.
Okay.
As a wave vibrates faster, its wavelength gets shorter. But a wave cannot have a wavelength that is shorter than the physical distance between the atoms themselves.
Because there's nothing there.
Exactly. If you try to force a wave to be any shorter or faster than that atomic spacing, it just doesn't physically map onto the lattice anymore. There's nothing in the empty space between the atoms to actually carry the wave.
Oh, wow. It's like trying to play a note on a guitar string that requires the string to be cut in half.
Precisely. Because there is a finite number of atoms in the box, there is a strictly finite number of ways they can move collectively.
You can literally count them.
You can. You can count the exact number of possible vibrational modes.
Right.
And once you reach the tightest, fastest possible vibration that the atomic spacing will mathematically allow, you hit the ceiling.
Whoa.
You cannot invent new, faster waves because you lack the geometric resolution. You have reached the Debye maximum frequency.
Okay, but to answer my own question earlier, where does the extra energy go if you keep pumping heat into the box?
It doesn't create faster frequencies, it creates larger amplitudes.
Amplitudes. So the waves get taller, not faster.
Exactly. The atoms swing wider and wider in their existing pathways.
Until what?
Until eventually the springs break, the atomic bonds shatter, and the material physically melts.
Oh, wow.
But while it is still a solid, that frequency speed limit is absolute.
That is an incredibly elegant synthesis of ideas right there.
Beautiful math.
Debye is basically saying that the solid acts like a continuous wave-carrying medium, but it's a medium made of finite dots, so the waves can only get so small.
You got it.
And by defining this maximum frequency, this absolute speed limit of heat, Debye finally had the mathematical framework required to test his model against Einstein's failure at absolute zero.
Yes.
He had to see if his web of connected springs actually matched reality in the deep freeze.
And to visualize how this mathematics perfectly solved the crisis, we need to look at what happens at the extremes of temperature.
Let's do it.
We need to visualize the chill.
Okay, let's focus intensely on a state where the temperature of a material is far, far below its natural capacity.
It is exceptionally cold.
Exceptional cold. To visualize this low temperature state, let's use a physical analogy.
I'm ready.
Imagine a massive, sprawling soccer stadium or, a huge indoor arena set up for a live concert.
Okay.
You are in the crowd.
Yeah.
And because it is a low temperature state, it's the very beginning of the event. The doors literally just opened.
So everyone is just getting to their seats.
Exactly. The vibe is quiet, the crowd is barely warmed up, and people are exhausted from the day.
Yeah.
There simply isn't enough overall energy in the venue for individuals to start violently jumping up and down in their seats.
Translating this to the atomic level, there is almost zero thermal energy in the crystal.
Right.
The atoms simply do not have the energetic juice required to activate those high-frequency, rapid, intense vibrations we just talked about.
They just don't have the energy tool.
Exactly. Those pathways are physically cut off to them.
So instead of chaotic jumping, what does an exhausted crowd do?
They do the wave.
They do the wave. They generate a slow, rolling stadium wave.
We've all seen it.
Right. It starts in one section, a few people slowly stand up, raise their arms, sit back down, and the motion transfers to the next section.
Right.
The wave travels slowly and majestically from one end of the stadium to the other.
It's very tame.
Exactly. In our crystal lattice, this rolling stadium wave represents low-frequency, long-wavelength phonons. It is a tame, gentle, highly cooperative collective movement.
And this slow, gentle movement is the exact mechanism that Einstein missed. Remember, Einstein's isolated pogo sticks froze out way too fast.
Right, because they couldn't share energy.
Exactly. But Debbie saw that even when the individual atoms lack the energy to jump independently, they can still participate in this massive low-energy collective wave.
They just go with the flow.
Right. This means the material holds onto a tiny bit of heat capacity, even at incredibly low temperatures.
Wow.
Debbie actually derived a specific formula for this frozen state, and it is known as the T-cubed law.
The T-cubed law, let's unpack that. It states that at extremely low temperatures, the specific heat capacity, that thermal sponge's ability to hold energy, drops drastically.
Yes.
And it drops proportional to the cube of the temperature.
Right, to the power of 3.
As the temperature shrinks, the capacity shrinks by a power of 3.
Yes.
But I have to ask, why a third power?
The great question.
Why not squared? Why not just a direct one-to-one drop? What does the cube represent in physical reality?
It actually represents the geometry of the universe we live in.
Wait, really?
Yeah,
Oh.
it comes down entirely to the three-dimensional nature of the crystal.
Okay, break that down for me.
Imagine you have a tiny, shrinking pool of available energy. Because we live in 3D space. We have up and down, left and right, forward and backward.
Right.
Any thermal wave has to travel through that three-dimensional volume.
So it's expanding out like a sphere.
Right. Now, as the temperature drops toward absolute zero, that available energy pool shrinks.
The tank is emptying.
Exactly. The high-energy, rapid vibrational modes simply freeze out. They become mathematically impossible to activate.
Okay.
Only the lowest energy, longest, slowest waves can survive.
The stadium wave.
Yes. And because these waves occupy a three-dimensional volume, the number of these accessible low-energy pathways shrinks proportionally to the volume they occupy.
I see.
In physics, we call this shrinking volume momentum space.
Momentum space.
Right, and because it's a three-dimensional volume, the available pathways shrink to the third power of the temperature.
So the geometry of space itself is severely cubically restricting how the heat can move.
Exactly. It's all about geometry.
Let me put myself back in that stadium to make sure I'm really internalizing this.
Go for it.
So I am in the freezing stadium. I am completely drained of energy.
It's cold.
I am way too tired to jump on my own, so I just sit there shivering slightly. My individual pathways for movement are frozen out. But when my neighbor slowly lifts their arms, it takes almost zero effort for me to just follow along and lift mine, passing the motion to the person on my left. Right, it's cooperative. The entire stadium acts as one massive, slow-moving unit because nobody has the individual energy to break the pattern. The 3D pathways for chaos are closed, so only the unified rolling wave remains.
That perfectly captures the mechanics of the T-cubed law.
Wow.
And the really profound triumph of Debbie's work is that when experimental physicists went back into the laboratory
Yeah.
and they took new measurements of materials at near absolute zero and plotted them against Debbie's T-cubed curve,
Did it work?
it matched flawlessly.
Oh, man, that's amazing.
The slow-rolling stadium waves completely solved the low-temperature mystery. The thermal sponge didn't just vanish, it shrank beautifully and predictably, according to the rules of 3D geometry.
It is an incredible moment of theoretical physics, just perfectly predicting physical reality.
It really is.
But the stadium doesn't stay quiet forever, right?
No, it certainly does not.
We've seen what happens when the venue is freezing, low energy, and restricted. But what happens when the team scores the winning goal in overtime?
Chaos.
Right. What happens when the headlining band takes the stage, the heavy bass drops, and the temperature skyrockets past that physical speed limit we established?
This brings us to the opposite extreme.
Hitting the ceiling.
Exactly. We are shifting our focus to a state where the temperature is far, far above the material's natural limits.
The game is won. The concert is at its absolute roaring peak.
The crowd is going wild.
Every single person, every single atom in that stadium is completely losing their minds.
Yep.
They are moshing, they are jumping, they are flailing wildly in every possible direction.
Yeah.
But crucially, bringing back the pixel monitor analogy, they are moving at the absolute maximum physical limit of their bodies and their space.
In the crystal lattice, this state represents hitting the W maximum frequency.
They've maxed out.
Completely. There is so much violent thermal energy pumping through the material that every single possible vibrational mode is fully activated.
Have we seen that?
Every single one. The slow rolling waves are still there, but layered on top of them are the most rapid, violent, localized shaking patterns allowed by the atomic bonds.
So it's just a mess of vibration.
Yes, every atom is vibrating as fast and as hard as physically possible given the geometric constraints of the box.
And this creates a fascinating bottleneck, doesn't it?
It does.
Because they have hit the physical limit of their atomic spacing, pumping the music louder in the stadium, which translates to adding even more heat to the material, cannot force the atoms to invent new ways to vibrate.
Nope. They are already executing every single move on the menu.
They are completely, totally saturated.
All the pathways are full.
And because they cannot invent new, faster vibrational modes to absorb that extra energy, the amount of energy required to raise the temperature of the material by 1 degree hits a flat, constant ceiling.
The capacity stops growing.
The thermal sponge is totally full. Adding more heat doesn't change the capacity, it just makes the water spill over the edges.
Exactly.
And this flat line has a historical name, right?
It does. It is the DeLong-Pettit law.
Oh!
The exact classical physics rule from 1819 that we talked about at the very beginning.
Wait, really?
Yes. The rule that said specific heat remains essentially constant.
Wait. So Dubby's incredible, complex quantum model of interconnected springs eventually just loops all the way back around to prove that the guys in 1819 were actually right all along.
They were right, but only for high temperatures.
Oh, I see.
This is why Debye's model is so historically powerful. A truly successful scientific theory doesn't just explain the new anomaly, right?
Right.
It has to naturally transition into explaining why the old theory worked in the first place.
That makes total sense.
Debye's model covers the entire thermal spectrum. At low temperatures, the modes freeze out and you get the T-cubed drop. But as you add heat, more and more modes activate, until eventually every mode is active, the stadium is maxed out, and the math naturally flattens out into the exact constant ceiling that DeLong and Pettit observed in their 19th century forges.
It bridges the gap between quantum strangeness and classical everyday reality.
Exactly.
But this raises a massive question.
Okay, what is it?
If every single material, iron, wood, glass, diamond, eventually hits this classical ceiling,
Yeah.
if every material eventually maxes out its stadium, flattens out, why do materials feel so completely different in the real world? Like, if I pick up a heavy piece of lead pipe, and then I pick up that diamond we talked about in the introduction,
Right.
and they're both sitting in my living room at 70 degrees Fahrenheit.
They feel totally different.
Right. They interact with heat wildly differently. Why, if they are both governed by the same ceiling?
Because while every material has a ceiling, the height of that ceiling is drastically different.
The height of the ceiling.
Yes. They all eventually reach maximum capacity, but the temperature at which they reach that maximum, the specific trigger point that transitions the material from the quiet stadium wave into the chaotic, maxed out mosh pit,
Right.
is completely unique to every single material.
The size of the stadium changes depending on what the material is made of.
Exactly.
And that specific trigger point, that boundary line temperature where the highest possible frequency mode is finally activated, that is the Debye temperature.
That is it. The Debye temperature is the universal thermal ruler.
The thermal ruler.
It is the threshold.
Yeah.
And to understand why this threshold changes from a piece of lead to a piece of diamond, we have to open the hood and look at the actual physical properties that build this ruler.
We need to figure out what controls the maximum frequency, what determines the absolute speed limit for a specific material.
Right.
And physics distills this down to two incredibly tangible physical properties.
Just two.
You don't need a PhD to understand them. The speed limit is determined by only two things.
Let's hear them.
Number one, the mass of the atoms. Are the individual atoms heavy or light?
Yep.
And number two, the force constant, or the bond strength between those atoms. Are they loosely tied together or rigidly bound?
Mass and bond strength. That is the entire secret to the thermal universe.
Just those two things?
Mathematically, the maximum frequency is proportional to the square root of the force constant divided by the mass.
Okay, let's pull that math out of the textbook and translate it into a physical feeling.
I think we need another analogy.
We do. We have mass and we have bond strength. Why does a heavy mass lower the frequency and why does a strong bond increase it? Let's use mattresses.
Mattresses. Okay, I'm intrigued.
Imagine a mattress, but not a normal memory foam mattress. Imagine a grid of objects connected by springs.
Okay.
Scenario A, you have a mattress made of incredibly heavy bowling balls.
Bowling balls.
Yes. Those bowling balls represent massive, heavy atoms, and these bowling balls are connected to each other by weak, stretched out floppy rubber bands.
Sloppy rubber bands. Okay.
That represents a very low bond strength. Now, if you take a sledgehammer and strike that mattress, what happens?
It's going to be a mess.
Exactly. The physical inertia of those heavy bowling balls fights against movement. They are hard to get going.
Right.
And the weak rubber bands don't have the tension to snap them back into place quickly.
Because they're floppy.
Right. So the entire mattress is going to jiggle, but it's going to be a very slow, sloppy, lethargic, lazy jiggle.
That paints quite a picture.
Heavy objects, weak springs, the absolute maximum speed they can possibly vibrate is very, very low.
It's severely limited.
Now, scenario B. Imagine a second mattress.
Okay.
This one is made of hollow, incredibly light ping pong balls.
Tiny mass.
Tiny mass. And instead of floppy rubber bands, these ping pong balls are tightly bound together by rigid, high-tension industrial steel springs.
A massive bond strength.
Exactly.
Yeah.
If you strike that mattress with a sledgehammer, those ping pong balls are going to vibrate incredibly fast.
Oh yeah, they blur.
The tension of the steel springs snaps the light balls back and forth violently. They will practically buzz into a blur.
Because there's no mass to hold them back.
Right. Light objects, strong springs. The maximum speed they can vibrate is astronomically high.
That physical intuition perfectly mirrors the quantum reality.
Really?
Yeah. The bowling ball mattress has a very low maximum frequency. Because its speed limit is so low, it takes very little heat energy to push those sloppy bowling balls to their absolute limit.
Oh, I see.
Therefore, it has a very low Debbie temperature. Its threshold for chaos is easily reached.
Right.
The ping pong ball mattress, however, has a massive maximum frequency. It can vibrate at blistering speeds.
Because of the steel springs?
Right. It takes a monumental, massive amount of thermal energy to finally force those tightly bound light spheres to reach their breaking point. It has a remarkably high Debbie temperature.
This relationship, mass versus bond strength, is exactly what makes the Debbie temperature a literal ruler.
It gives us a baseline.
Right, a baseline measurement for how any material in the universe will react to heat, based entirely on its structural integrity.
And this is where we bring it all home.
Yes.
We take this theoretical ruler and we test it on two of the most extreme physical materials in the natural world.
The ultimate showdown.
Exactly.
Yeah.
Put the sumo wrestlers up against the highly trained athletes.
Right.
Let's look at lead versus diamond.
Let's start with lead. Lead is the real-world equivalent of our bowling ball mattress.
It really is.
If you look at its atomic structure on the periodic table, lead is massive. It has extremely heavy atoms.
Very heavy.
And the metallic bonds connecting those heavy atoms are relatively loose and weak.
Think of the atoms in a lead crystal like an army of heavy sumo wrestlers.
Sumo wrestlers.
And they are tied together with those weak, flimsy elastic bands.
Right.
Because the sumo wrestlers possess so much mass and the bands have so little tension, their maximum vibration speed is incredibly low.
The result of this high mass and weak bonding is that lead has a shockingly low Debbie temperature.
Very low.
The threshold where it hits maximum chaos is roughly 105 Kelvin.
105 Kelvin. To put that in perspective, that is negative 168 degrees Celsius.
Wow.
Or roughly negative 270 degrees Fahrenheit.
That is freezing.
It is profoundly, dangerously, cryogenically cold.
It is the kind of cold you only find in deep space or specialized laboratories.
Yeah.
But for lead, that freezing temperature is its ultimate boundary line.
Right.
Even a tiny microscopic poke of heat at negative 168 degrees Celsius is enough thermal energy to cause those sumo wrestlers to hit their maximum sloppy vibration limit.
Exactly. At deep freeze temperatures, the lead sodium is already completely maxed out.
Now let's cross to the absolute opposite end of the thermal spectrum.
It's a diamond.
Let's look at diamond. Diamond is the ping pong ball mattress on absolute steroids.
It is.
Diamond is made purely of carbon atoms. Carbon is an extremely light element situated near the top of the periodic table.
Very small mass.
Right, the atomic mass is very small. And how are they bound together? Carbon atoms in a diamond structure form a three-dimensional lattice of covalent bonds.
The strongest bonds there are.
Exactly. These are arguably the strongest, tightest, most rigid chemical bonds in the natural universe. The force constant is massive.
So the analogy for diamond isn't sumo wrestlers. It's highly trained, feather-light, agile athletes. And they are tied together not with elastic, but with extremely tense, unbreakable steel cables.
Because the athletes are so incredibly light and the cables are pulled so impossibly tight, the frequency at which they can vibrate before breaking is astronomically high.
It is. They can buzz at incomprehensible quantum speeds.
The result is that diamond possesses an incredibly high Debbie temperature.
Super high.
While lead was maxing out and hitting its chaotic threshold at a freezing 105 Kelvin, diamond's Debbie temperature is roughly 2200 Kelvin.
2200 Kelvin. That is roughly 1900 degrees Celsius or nearly 3500 degrees Fahrenheit.
That is insanely hot.
You would literally need to drop the diamond into the roaring fires of an industrial blast furnace or the molten core of a volcano.
Just to max it out.
Yes. Just to inject enough thermal energy into the lattice to force those highly trained athletes to finally hit their maximum vibration limit.
Okay. We have established the two boundary lines. Lead taps out and goes chaotic at negative 168 Celsius. Diamond holds its structure until 1900 Celsius.
Right.
But here is the ultimate revelation. This is the moment where the abstract math finally explains the everyday world you and I live in.
It all comes together.
Let's look at these two materials sitting side by side at normal, everyday room temperature. Let's say 25 degrees Celsius or roughly 300 Kelvin.
Okay.
Let's look at the lead first.
For lead, an everyday room temperature of 300 Kelvin is a massive amount of heat.
Because it maxed out 105.
Exactly. It is nearly triple its debut temperature of 105 Kelvin.
So if we look at the stadium analogy,
The stadium is beyond packed. The concert is a riot. Every single sumo wrestler in that lattice is violently moshing, completely maxed out, vibrating at their absolute physical limit.
it is a chaotic, saturated mosh pit of thermal energy.
And what happens when a new heat wave, a new phonon, tries to travel through that chaotic mosh pit?
Right, say you hold a lighter to one side of the lead block, the heat wave tries to propagate through the metal.
It crashes almost immediately.
It crashes.
Yeah, and we need to explain physically why it crashes. When atoms are relatively still, they form a highly uniform, perfectly aligned grid.
Like a smooth road.
Exactly. A phonon wave can glide through that smooth grid easily, but in our lead block at room temperature, the atoms are swinging wildly out of their normal bounds.
They're exhibiting massive amplitudes.
The grid is completely distorted and warped.
It's like trying to drive a car on a road where the paving stones are randomly jumping 2 feet in the air.
That is exactly what it's like. When the incoming thermal wave hits that severely warped chaotic grid, the wave refracts.
It bounces.
It bounces back. It scatters. Physicists refer to this specific mechanism as unclap scattering, or U-process scattering.
Clap scattering.
The high-amplitude chaotic vibrations act as literal thermal breaks. The phonons crash into each other and deflect, severely blocking the smooth transfer of heat across the material.
The mosh pit is so violent and disorganized that a unified wave physically cannot pass through the crowd.
It just can't.
It just gets absorbed, deflected, and trapped by the chaos. Which means lead, compared to other metals, is a relatively poor, sluggish conductor of heat.
Now look at the diamond sitting on the exact same desk, in the exact same 300 Kelvin room.
For diamond, an everyday room temperature of 300 Kelvin is a joke.
A total joke.
It is barely a fraction of its 2200 Kelvin W limit.
Relative to its boundary line, room temperature is the deep, dark chill of the T-cubed zone.
Oh, wow.
To the diamond, your living room is an Arctic wasteland. The stadium is totally empty. It's quiet.
The athletes are asleep.
Basically, the highly trained athletes are barely moving. They're just generating those extremely slow, tame, rolling, low-frequency waves we talked about earlier. The rigid steel cables are holding everything in perfect, uniform alignment.
So what happens when a heat wave, a fun, enters the diamond stadium? Say, the heat from your fingertip touching the stone.
Because the stadium is freezing and quiet, and because the geometric grid of the carbon atoms is perfectly rigid and undistorted by chaos,
There are no thermal breaks.
none. The thermal wave can shoot straight across the material. It doesn't hit any jumping paving stones. There is virtually zero unclap scattering to block it.
So it just flies through.
The phonon travels completely unimpeded, like a high-speed bullet train on a perfectly smooth, frictionless, super express highway.
This is the massive realization. This is the answer to the hook we started with.
It is.
When you hold a real diamond against your skin, it feels surprisingly cold to the touch. It feels like a piece of ice that never melts.
Yeah.
And when you press it against your finger, it instantly steals the heat from your body. In fact, Diamond conducts heat faster and more efficiently than almost any metal on planet Earth.
It's incredible conductor.
And the reason it feels incredibly cool and conducts heat instantly is literally because, on an atomic level, its mass is so low and its bonds are so tight that it views room temperature as an absolute deep freeze.
Precisely.
Its internal stadium is entirely empty, so your body heat just rockets right through it.
It is the elegant, irrefutable conclusion of the physics.
Just beautiful.
Complex quantum states, the quantization of energy packets, the mathematical proportionality of atomic mass and bond tension, the continuum mechanics of wave propagation, the geometric restriction of 3D space.
It's a lot of math.
It is, but all of these abstract whiteboard concepts perfectly combine to predict the tangible, tactile, physical reality of holding that gem in your hand.
That's the best part.
Diamond feels cold because it is a superhighway for your body heat. And it is a superhighway because its Debbie temperature is so astronomically high that everyday human life is basically absolute zero to it.
That is just staggering. It takes this invisible graduate level math and puts it right onto your fingertips.
It really reframes things, doesn't it?
Completely. It completely reframes how I interact with the physical world. I look around my room right now, the metal microphone stand, the wooden desk, the glass window, and I realize they're all operating in entirely different thermal timelines.
It's the profound beauty of material science. By understanding the microscopic rules, we can fully manipulate the macroscopic world.
Right.
The Debbie temperature isn't just an abstract equation. It is the fundamental architectural blueprint of modern engineering.
Give me an example.
Well, it's the reason a cast iron frying pan is made of heavy metal to retain heat, but the handle is made of a polymer or wood with a completely different thermal threshold.
Oh, that makes sense.
It's the reason silicon, which has a high Debbie temperature similar to diamond, can be used to build microscopic computer chips that process massive amounts of electrical heat without melting instantly.
Without hitting that mosh pit state.
Exactly. It all comes down to knowing exactly where a material's specific stadium transitions from quiet waves to chaotic mosh pits.
Let's briefly recap this journey we've been on, tracking the history of human understanding here.
It's quite a journey.
We started in the early 1900s with classical physics breaking down the freezing cold. Albert Einstein attempted to save the day by imagining atoms as perfectly independent quantum pogo-sticking harmonizers.
Right.
It was a beautiful, elegant mathematical trick that ultimately shattered because it ignored the reality that matter is connected.
And from that brilliant failure, Peter W. realized that heat is not an individual sport. It is a collective wave.
Right.
But because matter is finite, those waves have an absolute speed limit.
That geometric speed limit dictated two distinct realities. At low freezing temperatures, the lack of energy restricts the crystal to slow rolling stadium waves, freezing out higher paths due to the limits of 3D geometry.
The T-cubed law.
The T-cube law, which solved Einstein's gap. And at high temperatures, the crystal hits the physical ceiling. Every atom moshes at its limit, completely saturating the thermal capacity.
Proving the classical Dulong-Pettit law.
Exactly. And finally, we discovered what builds the ceiling. The thermal ruler is dictated entirely by the mass of the atoms and the strength of their bonds.
Mass and bonds.
Heavy, loosely bound sumo wrestlers like lead max out quickly, turning a pleasant room temperature into a chaotic, heat-blocking, scattering mosh pit.
Clap scattering.
Right. While light, incredibly tightly bound athletes like Diamond require the heat of a volcano to max out, making room temperature feel like an empty stadium where heat waves travel completely unimpeded.
It is a seamless, beautiful story from quantum theory in 1907 to the touch of a stone in 2026.
It really is. But if we truly understand how this ruler works, it leaves us with a rather profound, almost science fiction implication for the future of engineering, doesn't it?
It absolutely does. Think about this logically. If a material's thermal reality, how it absorbs, blocks, or transmits heat, is entirely governed by its mass and the strength of its bonds.
Right.
What happens is we advance in synthetic materials science.
What do you mean?
What if we decide we don't have to accept the elements exactly as nature made them?
Oh, wow.
If we learn to artificially compress materials under immense synthetic laboratory pressure to force their atomic bonds to become infinitely tighter than a diamond.
Okay.
Or if we engineer artificial isotopes to manipulate the fundamental mass of the atoms themselves.
Could we do that?
Theoretically, yes. And if we did, could we design synthetic metamaterials with Debbie temperatures so impossibly high that they manipulate heat in ways we currently think violate the laws of physics?
That's incredible.
Could we build thermal superconductors that operate flawlessly inside the inferno of a spacecraft's jet engine without degrading.
We could essentially tailor-make the thermal universe to our exact specifications.
Exactly. The thermal ruler we've explored today isn't just a passive way to measure nature. It might actually be the exact blueprint we use to rewrite it.
A blueprint to rewrite nature's rules on heat. That is a wild, incredible thought to leave off on. Next time you pick up a piece of heavy metal or tap on a piece of glass or touch a diamond ring, just imagine the invisible stadium vibrating inside of it.
And ask yourself how close it is to the mosh pit.
Exactly. Thank you so much for coming along with us on this deep dive into the hidden world of the W temperature. We hope it sparked a little bit of that quantum drama in your everyday life. Keep wondering, keep looking closer, and we will catch you